But that implementation they can be topically or open. Topically, we have different technology. This is EndoCAD.
Hello everyone, good evening. Welcome to the first data analysis sessions. As we keep on waiting for the facilitator, we can keep on joining until after that the session has started. Madam Farida, if I'm audible to you, can you please start the session?
Hello, team.
Hello, madam. Welcome.
Thank you. I'm sorry I mixed up the link. I used a different link. That's why I was struggling to start a session. So as we agreed on our last session or previous session, today we are going to continue from where we stopped. So we did a data cleaning. So now we are going to do a data analysis, if I'm not mistaken.
Yes.
So let me share my screen. 7. Okay. I hope everyone can see my screen.
Yes, yes, you can see it.
Okay, so I hope everyone know how to open the do file and writing the command. So I'll just go directly. But today's session it will be more of practical analyzing data through Stata, and I will share this do file together with the data set that I'm using so that we can all understand and all be at par. So tomorrow's session will be based on pitfalls on data analysis. So today we're going to do the analysis as well as interpretation. And tomorrow, Mr. Titus will be discussing about the pitfalls. And then on Sunday, we'll have our assignments. Then I think this week will be all for the data analysis. So I'm using a different data set. So I'll just import the data here. Then after importing, to be sure that my data set was imported first, here I cannot see the rates. So if I see rates, that means there is a mistake in my command and so on. So since it's not read and I can see my variables here, then I can assume that my data is correctly imported. Following by that, this command, I think we discussed it on our previous session. It's all about analyzing how many variables we have. So in this data set, we have 10 to 9 variables. So going forward to the code book, we want to see which variable has missing values, etc. So in here, you can easily see that we had participant ID, but we don't have a missing value. And this is a unique identification. So we have 1 to 20. Then the second variable is age. Let me expand it. Expand this. So we have age, and age range from 23 to 54. And we don't have missing, and it is a numeric variable. And we have these percentiles, 10 percentile, 25, 50 percentile, which can be presented as median, 75%. Gender is a string variable that is categorical variable, which is a nominal scale, in nominal scale. And it has only 2 categories, females and male, and we don't have any missing value in this variable. Also, we have height. So it's numeric, and it range from 157 to 178. And we have a mean for height together with the percentiles, and we don't have missing. So also in weight, we don't have missing. We just only have, it's range from 54 to 81. And systolic blood pressure, 110 to 140. But almost in all the variables, we don't have a missing value. And this disease status is our outcome variable. So we have no disease and yes disease, and it is a categorical variable. So in this is just, this is all about explaining our data sets or understanding our data set, what kind of variables do we have, and so on. So after analyzing, cleaning your data, you have to analyze them. And in analyzing them, before going to answer your research question, you need to understand, or you need to perform, we need to understand the characteristics. For example, in your research section, we expect you to see if you have a social demographic characteristics table that explain maybe age range from which, and mean age, and so on, percentiles for categorical variables. So sometimes we might present a variable in tables, for example, that social demographic table, and I think everyone sees it, maybe not now, but previously. So for example, if you want to determine a frequency, for example, we want to know how many are females and how many are males, and they consist of how many percentage. So if you write tab gender, then you obtain a table like this. So you have, we know that females are 14, so, and 6 are males, and in percentiles, or in percentage, females are 70% and males are 30%. But sometimes you may wish to have a graph instead of tables. So for example, if I want to draw just a bar graph to represent frequencies, then I'll have this kind of a graph. This one. So we have females, and here are percentage for these groups. So we have females and males, and you can see it's females are 70% and males are 30%. So but the bar graph is used for categorical variable. In previous session, we learned about characteristics or types of variables, whereby we learn qualitative and quantitative. So qualitative, it's all about when the data is expressed in words. For example, in gender, we have males, females, or we have smoking status as a variable, which consists of smoker and non-smoker. Or disease status, yes or no. All of these are categorical or qualitative variables. But if we're talking about quantitative variables, it means variables which are continuous, which can be age, height, weight, systolic, and diastolic in presence in this data. So in graph presentation, bar graph is used for qualitative data, and for quantitative data, we use a histogram. So, and this graph may have different uses. For example, in histogram, there are some tests that will require you to assume a normal distribution for the variable. So histogram can give you a direction or hints if a variable is normally distributed or not, so that you can perform a specific test that you want to conduct. So by saying so, in this data presentation, I'll explain these 4 graphs, graph, bar graph, histogram, and box plot. And why are we running the box plot? If we are running box plot, we want to see if in our variable, numerical variable, do we have any outliers? And when I'm talking about outliers, I mean those variables or those values now in a variable that are far from the mean. For example, in age, I collect the age, maybe 23 up to 44, but maybe majority, if I draw my box plot, I expect to have most of individuals falling from 23 to 54. But if it happened, one individual is 80 years old, then this is an outlier because this individual is far from the average or far from what is present from the data. So it might be, and this might be an indication if this age was correctly inputted, or during a data collection, someone, the data collector ask or give interview wrong person, because in here, majority are from 23 to 54. So if we have seen 80, this is an outlier because he was far apart from what was observed. So this box plot, first also, that's the first function of the box plot. The second function of it is just giving you the first quantile, second quantile, which is a median, and third quantile. So let me draw a box plot for age. So in here we can see this part represent first quartile, and this part present second quantile, which is a median, and this one is the third quantile, and this edge is fourth quantile. So if we observe any point around here or here, then it is an outlier. So this is just for one variable, but sometimes you want to see outliers, or you want to see how distribution for a certain variable over categories of another variable, also possible with a box plot. So here, before I run the code, is there any question about tables, graphs, for bar graph, histogram, and box plot? Is there any question? So let me assume there is no question. So here we see the distribution for the gender. We have 70% of the respondents are female and 30% are male. But in presenting this, you just say most of the respondents in this study were female, and you put it in the bracket 70%. But this is our variable, outcome variable, disease status. So we have 14 respondents who are diseased, and you have only 6 respondents who are not diseased. And for the smoking status, we can clearly observe that 50% were smokers and 45% were non-smokers. And here is corresponding. Oh. So this is for non-smokers, we have 45%, and smokers were 55%. Then for disease status, 30% were not diseased and 70% were diseased. So looking back to this histogram, for age, it is almost normally distributed because let me see if I can draw. For a normal distribution curve, it has to be like this. How can I do that? I don't know how can I draw it here, but for a normal distribution, it has to be like a bell-shaped curve for us to say it is normally distributed. But in this graph, we can see it is almost approximately normal distribution for age. And for this height, it is a skewed bit because we see that we have high, then it keeps decreasing. And for weight, it's not normal because you have this, it decreases and it's ups again, and so on. So for the box plot, as I explained, you can just draw it for a one variable or for one variable, continuous variable over categorical variable. So here, I want to see the distribution of age between the diseased and participants who are not diseased. I can clearly observe it in this group. There is this outlier here who is almost maybe age 48, while in this diseased group, there is no outlier. So here can be detected as outlier. Come back to height. There is no outlier. So it is, but we can just see it. If we have to assess the distribution between the two groups, we can clearly say this for those who are not diseased, their heights are not normally distributed because here we see it is very short, but in here it is very large. It has high interval compared to this part. So what does it mean? It means the majority of the respondents in for those who are not diseased, most of the respondents in that group, their heights are between 158, maybe 158 to 159. And here it is normally distributed because we almost have equal distribution for this. And for the weight, here we have this, and we can see that this one is outlying observation because it's almost here in 74 years, in 74 kg, while most of the respondents in this group lies from maybe 53 to 60. So this was just a data presentation for us to clearly see how our data looks like. But sometimes in your table, since you have to present age, sometimes you may present it as groups, maybe young adults and young adults and children, or you may categorize it, or you may just take as a mean for it, maybe a mean age and a standard deviation. So to get mean and standard deviation, if you want to present a mean, so you can just this code. Then I'll just pick weight. So we have weight here, and then you have percentiles. we have smallest value and largest values, but our interest is this one, because we want to see the mean and standard deviation. Standard deviation tell us how far these individuals are apart, and mean is just on the average. The participant mean weight is 66.3. So these are just descriptive statistic. So going back, before I go to objectives, because these are just preliminary or just descriptive statistics, and then we move forward to our objectives, whereby you're going just to say, if you want to compare, maybe you want to compare the height between those who are diseased and those who are not diseased, or you want to compare diastolic and systolic between those who are diseased and who are not diseased. Or sometimes you want to just measure, you want to find if there is any association or relationship between two variables. And for a chi-square, so we have for comparison, you have t-test. If you have these two variables which are quantitative, then you have to use a t-test. But if you compare, you want to find an association between two categorical or qualitative variable, then you are going to use a chi-square. And if you are looking for factors associated with your outcome, that is where you are going to fit a regression. But if you have a binary outcome, for example, in this case of today, we have disease status yes and no, then you are going to use binary logistic regression. So today's session will be more on t-test, on how we can implement a t-test when our research objective is to compare. We just need to compare if there is any difference between the two groups. And sometimes t-test is used when we want to compare the intervention that have been made. For example, you have a certain drug, you want to assess if it perform well compared to the other one. Then you want to see its impact on systolic or diastolic blood pressure or BMI. You can just pick any variable that you want to assess before the intervention and after intervention. So if you want to assess intervention, you need to have a data before intervention and data after intervention. So if you want to assess blood pressure, then you just measure your diastolic and systolic blood pressure before, and then you are going to conduct the intervention. Then after intervention, you are going to collect again diastolic and systolic blood pressure. Then after taking these two observations, then you need to compare if they are the same or not. And why do we have to compare? The intervention that we have to implement, it has to be, you have to know, or you have to understand the direction which you are heading to. Is this intervention aimed at reducing this systolic and diastolic, or aim at increasing this diastolic and systolic? So if it aims in decreasing or increasing, we can just see, for example, if we know we want to see it if it's increasing, then we know that since the default is taking the before minus after, then it will means if we aim at increasing, then we are looking at our alternative will be on the left side. But if it is we aim at decreasing, then it will just be our alternative hypothesis will be on right side. And what do I mean by saying left side or right side? What I mean is, for example, when formulating the hypothesis, especially for comparing the two groups, and hypothesis is just our assumption. In the null assumption that we have to carry on, this is null hypothesis, is there is no difference between before measurements and after measurements. So in other words, or in simple words, we can say that this intervention has no impact. That's why if we take before measurements and after measurements, it's 0. The difference between the two is 0. Then the intervention that has been implemented has no impact. But if we intervention has impact, then what is the direction? Is it going to increase this diastolic blood pressure, or is it going to reduce it? If it is going to increase, and for us to say this intervention is working, we want to assume if this diastolic is increasing, then why am I saying it to be on a negative side? Because if we take before minus after, it will just be negative. Because if intervention is working, if we take, for example, the diastolic, the first before intervention is 20, and after intervention, we expect it to be maybe 130. So 125 minus 130 is -5. So almost it will just be less than 0. So it will be on our left side. Because we have, let me try to draw in our documents. So let's assume we have this kind. And this is our 0. So this means there is no difference. That means if we take our measurements before minus measurement after, there is no difference. That's why it is 0. But it might happen if our aim is increasing. That's this before, maybe let's say 125. This is 130. Then if it's increasing, then the alternative hypothesis will be on this side. That means if we take measurement from before minus measurement after will be equals to negative. This is left and this is right. So, but if we aim at decreasing, then let's say it is 120 and this is 120. So it will be 125 minus 120 is positive. So on the right side, if we take measurement before minus measurement after will be equals to positive. So this is our left and this is our right. And here is our null. Clinically, since we are dealing with humans, then it is recommended to clearly explain the direction of the measurements. Do you want it on the left side or right side? Because sometimes if it, in order for us to say people are healing, it is on the left side and we didn't consider it. And then maybe if we are using a two-tail, A two-tail means we don't have any direction. It might be on this side, on the right side, or it might be on the left side. So we only saying if we take measurement before minus measurement after is not equal to 0. So having this kind of alternative hypothesis, it might harm individuals or patients in the later stage, because if increasing this BMI may worsen a situation or may make a situation being severe, then we are going to make this mistake by saying intervention worked while it wasn't. Before I proceed, is there any question? No, I see one question in the chat. Any question? Okay, Ndaki, you can unmute and proceed.
Okay, my question is that you have previously discussing about that when we are dealing with humans, maybe we'll be recording somehow by later giving explanations. Now, why
Yes.
why did you give some expectations that when we are dealing with humans, maybe we do like this? What about those maybe dealing with animals? How are they supposed to do?
Okay, so what I was suggesting is it is better to have direction, whether it is left or right. But if you are dealing with something, for example, if it is animal, also you have to be careful because they also possess lives. But for example, if you just want to assess whether a certain factor is associated with a certain disease, you can just assume both sides, because people maybe to, sorry, my internet. So to just give an advice to people, maybe to abstain from that factor or to keep doing that factor. So not only in human, but also in animals, but also having a suggestion of whether left, right, or two-tail is also based on your assumptions and your research questions, because I believe before you formulate your question, you did a literature review and so you understand which one is preferred based on your area of study. Did I answer you well, or you need more clarification?
Yes, thank you. You answered me very well.
Okay, another question? So that was for comparison. if you are dealing with intervention or you just want to compare, for example, if I want to compare height or weight for those who are diseased, then I need to specify my null hypothesis and alternative hypothesis beforehand. So sometimes you just need to find an association or relationship between the two variables. For example, if you want to find if there is any relationship between disease status and smoking status. Since these two variables are categorical, this is yes, no, and this is yes, no, then you can just use chi-square to implement that. So in chi-square, we have in chi-square result, you just obtain your p-value. Then after obtaining it, if it is less than 0.05, then we can assume that there is a relationship between the two variables. But sometimes you want to see, or you want to clearly telling people whether in which direction these two variables are associated, then you have to conduct a logistic regression. In logistic, regression is applied when you have a binary yes, no question. So why logistic? Chi-square, it will just tell you there is an association or relationship between disease status and smoking status. But it will not tell you whether it is this smoking status, whether it is protective or harmful. So to get those results, you need to perform a logistic regression. And in logistic, it will just give you the odds. That the odds, for example, you get smoking status after fitting it as 0.7, then we say that, or 2.7, let's say smoking status as 1.7. Then in interpretation, we can just say that those who are smoking, their chance of getting disease is 70%. Why 70%? Because this one is our null variable. And why is null variable? That means when we say null, that means there is no association. So greater than 1, that means it increases, and less than 1, it is decreasing. So why 1? That means because in smoking status we have yes, no. So we finding the ratio of having one disease between the two. So if they are 0.2, then it will just be 1. That's why we see that smoking status, if it is 1, we can just say there is no association between smoking status and disease status. But having 1.7, since it is increasing, then we can just say, is someone talking? Okay, maybe it's my mistake. Then this, what is increasing, -1, it will remain as 0.7. But if you are telling someone 0.7 it might be misunderstanding, but if it will be clearly, if you say 70%, it is easier to understand in percentage than in decimals. So this is how logistic is interpreted, and also it is just 0.05 if it is significant or not. So before going back to the command starter code, is there any question? So if there is no question, I'll just run this command. So we have here, we just want to compare the height by disease status, whether height having any impact on disease status. So I'll just run it. So groups, we have two groups, that is those who are diseased and those who are not diseased. And there are 6 individuals who are not diseased, and there are 14 individuals who are diseased. And these are their respective mean and standard errors. But this is our interest, confidence, this is the confidence interval. But here, since if we assume left side, that means mean height for those who have disease and the height for those who haven't the disease is less than 0, then this is a p-value that we are going to interpret. It is 0.0180. So we can just say there is a significant difference between the two means in disease status for the height and those who are diseased and those who are not diseased. So in here, if we don't know the direction and we decided to go on with this, then we can just say there is a difference between mean heights for those who are diseased and those who are not diseased. But in this left side, we need to say the mean height for those who are not diseased is lower compared to the mean height for those who are diseased. And here, if we look at this p-value, if we assume the right side, then it's clearly here, it is not less than 0.05, then it is not significant. So, this is a sample code if you have observation before and after, because here it is just, you are just before and after, but in the data set that I have, I don't have it, so I just assume my height to be my first observation and weight to be my second observation. So let us assume this height is height before observation, and this height should weight height after intervention. So if you have your data set that maybe you have before and after, and you want to measure you want to compare, or you want to compare those two means in order to assess whether the intervention is working or not, then you can just specify your variables here, then you run it. So it is just the same as the previous one. We have 3 alternatives, and the software cannot give you a single p-value because your alternative hypothesis may be different from, maybe it might be less than or not equal or greater than. That's why it gives you all the three. But when fitting model, the one that is used is not equal, because a model will give you both direction. It might be this way or that way. And in your comment, you may comment whether this is protective or harmful. So this is chi-square. So let me use the smoking status. Then if I run this, I'll just get this. So it will just say for p-value is 0.001. So there is a very high significant association between smoking status and disease status. Before I move forward to univariate and multivariate binary logistic regression, if there are any questions based on the results provided or more clarifications on results, or everything is clear. Let me see chat, see if there is any question. I don't see a question. Okay, Julie.
I don't have a question, madam.
Okay. Oh, you don't have. And I saw a hint from Sarah Kelvin. Sarah?
I mean, it was not a question, but I understood, so I clapped the ends.
Oh, okay. So let's move to logistic. So one thing you have to note in starter, your variable, you need to code your variable. If it is binary, then you have to specify it as 1, 0. Or if it is category for more than one, then you need to record them as 1, 2, 3. So this command is for a variable which is binary. So you just need to specify here. So here it will be smoking status. So the word that you put here in quotes is the one that will be labeled as 1. So we all heard about univariate, multivariate, etc. Though statistically, if you say multivariate, it's not the same context as we interpret it. In statistical, multivariate means when you have multiple outcome variable, but multivariate we are using in our context here, maybe in Kohas or many researchers, multivariate means when you have more than one independent variable. So in order to run a logistic, you can just, for univariate, that means you are going to add only one variable because it is univariate, only one variable. So for example, I started with age here. Oh, I didn't run the code, sorry. Here. And this one. Oh, here. Sometimes if you forget, instead of putting a capital, you put a small one, it will not run. So here, So this is a result for one univariate. As I explained, it's odds ratio, and this is a continuous variable, which is age. So an interpretation, if you look at our p-value, it is not significant, but let's forget about p. Let's focus only on interpretation. For example, if you have, let's assume it's significant. And then you have this odds ratio, 1.04. That means as age increasing, the odds of having the disease is increased by 4% because it is 1.04. So if we multiply by 100, it is 4. So the odds of having the disease is 4%. So since this is continuous, then we have to say, since this age represented in years, so 1 year increase results into increase in the odds of having the disease by 4%. So what if we have a categorical variable? Let's say this. Then we just see we have, oh, okay. So this one, we have 1 and it is omitted. Do you know why? Or should I explain? Can someone try or I explain? So this can be observed because if you try to just tabulate these two, you find out that there is 0 in a table. That's why we have 1. So let us taking any other variable, for example, gender, to which we don't have 0. So if you're having this kind of a table, 0 here, and you run your logistic, it will just be omit them and give you odds of 1. And this is the reason why, because in finding odds, we need to divide these numbers within the cell. So if we try to divide it, there is 0. So it cannot divide it anymore. That's why it gives you 1 and it is omitting it. No. Yeah. Gender and I put 3. Okay. So now let's do a logistic. Status. Gender. Binary. Okay, we have 0 here, but let me create a new variable. generate no smoking, no smoke equals to 1. Then like this, smoke equals to 1 if smoking equals to 0 if smoking mm, mm, no, it's 8. Repito. Sorry, I'm creating a new variable since where is it? This I have this. I want to create a categorical variable to which it will not have contain zeros, so that we can see how we can interpret okay, now we have this table. So just smoke. Now we have 1, which is very little. Anyway, but the essence of it, in interpreting the categorical value, is different when we are interpreting for our numerical. For our numeric, let's say 8. We say 1 unit increase ita result kwenye, kwa mfano kama if you get 1.43, then it will just increase the odds of having the disease by 43%. But if we are dealing with categorical, let's say we have smoking status, which is yes, no. So if we put it this as 1 and 0, this is our reference group. So if we have odds ratio of 1.73, then it will just be for those who are smoking. For those who are smoking, their odds of they have higher odds of getting the disease by 73% compared to those who are not smoking. So the interpretations differed from the continuous one. In continuous, we say 1 unit increase or 1 year increase or 1 kilogram increase in weight will increase or will decrease the odds of getting or having the disease by this percent. But if we have a binary independent variable, for example, smoking, then we just say for those who are smoking, their odds of having the disease is 73%, which is higher compared to those who are not smoking. But sometimes you might have a categorical variable, let's say education level, which have 1, 2, 3. Maybe this one is primary, this is secondary, this is tertiary. So this one will be taken as reference group. So let's say in secondary you have 1.4, and in tertiary you have 1.6. Then in your interpretation, you just say for those who are secondary, who have secondary education, their odds of having the disease, maybe let's say now let's us look at different direction, let's say decrease. So for those who acquire secondary education, their odds of having the disease is decreasing by 60%, because it will be 1 minus 0.4 times 100, since it is decreasing. So 60% compared to those who are in acquire primary education. So this will be your reference group when interpreting for those who are in secondary compared to those acquire primary education. When you come to tertiary, you just say for those who acquire tertiary education, their odds of having the disease is lower by this percent compared to primary education. Up to that point, are we together?
Yes, Madam Yao.
Okay, so I'm sorry, let me turn on the light. So moving to multivariate, the interpretation will just remain the same, but the difference, you need to add adjusting for the other variables. You can just mention it, or you can just adjust, or we can just say adjusting for other independent variables. So moving forward to this, so you can either feature a binary logistic regression using logistic, or you can just use GLM, but let me not complicate the issue. There is a reason behind why you have to use GLM, because sometimes you may run your logistic and you obtain a very, for example here, you see this confidence interval, it's very big interval. So you need to use GLM to be precise. In fitting GLM, it is just, you need to specify a distribution as binomial. So, and link is logit, because after fitting it, it will just give a coefficient. Then you need to use this command in order to get those odds ratio. So let's keep using logistic. Then you have our disease status as outcome. Then let's put height, age, weight, BP, diastolic, BP, systolic. Then if we run this code, that is height, weight. Okay, this one. Oh, here. Okay. Let's see. Majestic. And then we have H. Okay. Alright. Oh, majestic. And then you have disease binary. And then you have age. You have height. BP systolic. So if you run your multivariate, you obtain your results and it just say an increase, now it decreases. So you can just, when we run logistic with age, the disease binary, with age, we get 1.0. But now after adjusting for height, blood pressure, it becomes less, which means it decreasing. As unit increase, it decreases the age. This is just because of the presence of other factors. I'm not sure if you learned about confounders. Have you learned about them? Do you know what confounders is? You know it? Okay. So maybe there is a variable here, which is a confounder. So it confound the effect of age. That's why we see here it increasing the chance of having the disease. But now adjusting for the other variables, it decreases the chance of having the disease. So any question?
I have a question.
Okay, you can proceed. You can ask.
Okay, I wanted to know, for example, in your table, there is no, the p-values are all greater than the 0.05. Can you still
Yes.
use those results to say anything? Or we are just
No.
using it for learning? For example, the
Yeah,
odds
this is
ratio.
okay. This study, I'm sorry if you have not finished, you can finish, then I will answer. Or have you finished? Okay, then I'll assume you have finished your question. So this is just for learning purpose. because these p-values are not significant. So what I was just doing is just we have to understand on how we can interpret data, how we can interpret the result from the logistic regression, result from a chi-square, or result from a t-test. So this is just only for the learning purposes, but in your studies, in order for you to comment about the odds ratio, you need to experience a significant p-value. Any other question? Or do I have to assume you understand? Do you understand very well or moderate?
Yes, we understand.
Okay. Then I'll share this code together with the data set so that you can keep plan, practice, and you have hands-on practicals so that you can understand. I think by doing more practicals, you can also decide to use a different data set, maybe the data set you have, and you try to do a t-test, you decided to do a chi-square or univariate analysis and multivariate analysis. So by saying so, today I think we finished early. So before we close the session, if there is any burning question or burning issues, you can just present.
Sorry, I think it's my internet is bad, but my Zoom keep disconnecting. I don't know if everybody's experiencing. But I was confirming if you said that we are going to answer that question at the end.
Yes, we will have an assignment, which I provide you with the data set, and I'll just give you objectives, then you analyze it.
Okay. I also wanted to ask another question.
Mm-hmm.
So when you use, let's say, SPSS, it's going to give the same results, yes? If you are analyzing. So there was this prompt that SPSS was bringing for when I was trying to run the chi-square test, and it was telling me that if some fields are less than a certain amount, that I cannot actually use, I cannot interpret the data correctly. I wanted to know if there is any prerequisite when you are running a chi-square test to the 4x4 table, like in terms of the number of. Yeah, I don't know if you've got the question.
Yes, I got your question. In order to use a chi-square, because this data is the one just I simulated, and I simulated only 20 observations. So in order to perform a chi-square test, in your two tables, your values or numbers or frequencies inside the table has to exceed 5. So if it does not exceed 5, it's advised to use a Fisher's exact test and not a chi-square, because these two tests will just give you same answer or same interpretation. But chi-square require more observation compared to Fisher's exact. And in Fisher's exact, you can even have 0 inside and you can still get answers.
Thank you.
And by asking that, I think I will just add also the command for Fisher exact test in the do file. Then I'll share it with you. Any other question? Okay, then if there is no question, let me return the floor to our host.
Yeah.
Okay, thank you so much, Madam, for today's patience. I hope
Okay.
everyone who joined was able to learn. Let's meet tomorrow at 6 p.m. as usual for the next session. Thank you.
Thank you everyone for your participation.
I'm not